Hello everyone. Today we are going to learn about Chapter 3, Discrete Random Variables and their probability distribution. In Chapter 2, we have learned basics of probabilities. So from this chapter and the following chapter, in Chapter 4, we were going to learn about discrete random variables and continuous random variables and their related probability distributions. Okay. Chapter 3.1 talks about basic definition. So in definition 3.1, a random variable y is said to be discrete if it can assume only a finite or countably infinite number of distinct values. Okay, so this is the definition for discrete random variable y. And the events of interest are often numerical events that correspond to values of discrete random variables, like dice or tossing coins, or if it have head or tail, and um, those kind of discrete events can be related to discrete random variable. Certain types of random variables occur so frequently in practice, such as rolling a dice or flipping a coin. Those kind of random variables occur so frequently and useful to have. So it is useful to have the probability for each value of a random variable. Okay. And this collection of probabilities is called the probability distribution of the discrete random variable. So this is why we are going to learn about discrete random variables and their related probabilities. Okay. Okay, let's look at the example 3.1. A supervisor in a manufacturing plant has 3 men and 3 women working for him. He wants to choose 2 workers for a special job. Okay, and not wishing to show any biases in his selection, he decides to select the 2 workers at random. Let Y denote the number of women in his selection. Find the probability distribution for Y. Okay, so here a supervisor is choosing 2 workers from 6 workers. So what is experiment here? Experiment is choosing 2 workers from 6 workers, 3 men and 3 women. And what would be a simple event? Simple event is randomly choosing 2 workers among 6. So for example, male 1 and male 3, if you choose this way, that's one of 6 events. And how many events do we have? It's 6 choose 2. So there's 15 ways of a simple event. And let's check the event related to random variable y. So random variable y denotes the number of women in his selection. So for example, event y equals 0 is choosing two member or 2 member from men and no one from woman. So this is 3 choose 0 and times 3 choose 2, which is 1 times 3, and it have 3 samples for event y equals 0. And what about other events? So for event y equals 0, the related probability is this thing. Since we are choosing workers equally likely, the chance is same. The chance for all simple events is all same. It's 1 over 15. And so P0, probability of random variable y equals 0, is 1 over 5. And what about event 1 and 2? For event 1, we need to choose one member from 3 men and one member from 3 women. So it's 3 choose 1 times 3 choose 1. So it's 9 over 15. And so it's the probability of random variable y equal to 1 is 3 over 5. And for event y equals 2, similarly, for men, it's 3 choose 0. For man, it's 3 choose 0. And for woman, it's 3 choose 2. So it's 1 over 5 is the probability related to random variable y. Okay, and here's the table for this situation. Here's our random variable y, and this is the number of women in his selection, and it's discrete event y. The possible y are 0, 1, and 2, and the related probability is 1 over 5, 3 over 5, 1 over 5, and we can also make probability histogram for table 3.1. Okay. Okay, here is theorem 3.1. For any discrete probability distribution, the following must be true. Okay, so the first one is the probability measure of y is greater than or equal to 0 and less than or equal to 1 for all y, and the sum of all probability measure y equals 1, where the summation is over all values of y with non-zero probabilities. Um, Actually, to see this is true, you just recall the axiom of the probability and the random variable y. Actually, random variable y. This is a function from set to a real value y. Uh, the random variable y from the set it's a function from set to real value. So uh, it 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 would be natural extension to random variable case from the axiom of the probabilities to the random variable situation. Okay, so you can check theorem 3.1 from this axiom. Okay, and the homework for 3.2 is these. Okay, chapter 3.3 is about the expected value of a random variable or a function of random variable. Definition 3.4 is about the definition of expected value. Let y be a discrete random variable with the probability function py. Then the expected value of y, ey, is defined to be this way. Ey equals the sum of y times py. And actually, if py is an accurate characterization, then the ey would be mu, the sample mean mu, population mean mu, and it's completely consistent with the definition of the mean. The definition of the mean is this one. And how these two are related, I will explain it from the example in the next slide. Here is our example, the probability distribution for y, for y 0, 1, 2, for discrete values of y's, the probability associated to these value is 1 over 4, 1 over 2, and 1 over 4. And let's say that the experiment were conducted 4 million times. Then what would be the mean? By definition of the mean, it's we conducted this 4 million times. So here our n is 4 million, and by mean, the expected number for uh, observing 0 would be 1 million. Since the probability of y is 1 over 4, the expected number for observing 0 would be 1 million, and also observing 1 is 2 million, and observing 2 would be 1 million. And actually this is same as the definition of expected value. I mean the 3.1, its summation of y equals 0 to 2, y times probability py. Okay. Okay, Theorem 3.2 talks about function of expected value of function of random variable. Let y be a discrete random variable with probability function py and gy be a real valued function of y. Then the expected value of gy is given by this equation. And actually, this is very natural because the random variable y. What is random variable y? This random variable y is functional from set, from set, from set to a real value. Random variable defined on event set of simple events to the real value, and this gy is uh, this function g. This is a function from real value to real value. So actually this gy is again random variable from the domain of sets to the real value. So gy is again random variable associated with the same probability distribution of y. So you can just think of this gy as z. Again, this z is a discrete random variable, new discrete random variable, and the associated probability is again py, and this random variable g have value gy for each set. The here y have value y, and for g of y it have gy. So this one holds from that. Here is definition 3.5. If y is a random variable with mean expected value of y equals mu, the variance of a random variable y is defined to be the expected value of y minus mu squared. That is, variance of y is expected value of y minus mu squared. The standard deviation of y is the positive square root of vy. Okay, it's the definition for the variance. So if py is an accurate characterization, then we already know this. E of y is mu, and vy equals sigma square. And let's move to the example 3.2. The probability distribution for a random variable y is given in table 3.3. Find the mean, variance, and standard deviation of y. Okay. Here's our random variable y. It's discrete random variable. It have the possible values are 0, 1, 2, and 3, and related probabilities are 1 over 8, 1 over 4, 3 over 8, and 1 over 4. Okay, and let's calculate one by one. By definition, the mu EY can be calculated this way. The sum of all y, y equals 0, 1, 2, 3, and and times probability of y. So for y equals 0, the related probability is 1 over 8, and plus for y equals 1, the related probability is 1 over 4, and plus when y is 2, the related probability is 3 over 8, and for y is 3, the related probability is 1 over 4. So when we are calculate this, we can get 1.75. So the mu is 1.75 here. And let's calculate the variance and the standard deviation. The variance is expected value of y minus mu square. And the definition here is that summation of y equals 0 to 3 and y minus mu squared times the probability measure. So y minus mu square, when y equals 0, y minus mu square is this term, and the probability measure for this is 1 over 8. And for the second term, when y equals 1, 1 minus 1.75 squared times the related probability measure is 1 over 4, plus and when y equals 2, 2 minus 1.75 squared and times 3 over 8, and lastly 3 minus 1.75 squared and 1 over and times the probability measure for that 1 over 4, and as a result the sigma sigma square is this one, 0.9375. And to calculate standard deviation of y, we can get the square root of this one. Then we will get the standard deviation for y. And here is theorem 3.3. Let y be a discrete random variable with probability function py and c be a constant. Then the expected value of c equals c. Expected value of constant is just constant. And why is it true? Consider the function gy equals constant. Then by theorem 3.2, the EC is EGY, and from the definition, sum of y c times py equals c times sum of y py, and from the definition 3.1, no, that theorem 3.1, I think. This one is equals to 0. Sum of all probability measure equals 0, so it's C. So that's why this theorem 3.3 holds. And here's theorem 3.4. Let y be a discrete random variable with probability function py. Gy be a function of y and c be a constant. Then expected value of c times gy equals c times expected value of gy. So this theorem tells us that the constant can go outside of the expectation. Let's look at why this is true. By theorem 3.2, we can express this way: expected value of c times gy. Since this is another random variable, we can express this as this way. And here's constant, and constant can go outside of the summation, and so this one holds, and this one is expected value of gy, so the theorem 3.4 holds. Okay, and let's move on to theorem 3.5. Let y be a discrete random variable with probability function py and g1y, g2y, gky, bk functions of y, then the expected value of sum of all functions g1y to gky, it is equal to expected value of g1y plus expected value of g2y, yeah, this is hold. And to prove this, we can just use the previous theorem, 3.2. Since expected value, actually this is sum of something, and okay, let's just look at this case for k equals 2, and this can be expanded to the k case. For k equals 2, by 3.2, the expected value of g1y plus g2y is equal to sum of y. We can express this as this way, and actually from here we can divide these two summations, so it can be divided this way, and for each of the summations can be expressed as each expected terms. So this is hold for k equals 2, and actually you can extend this to an arbitrary number of k by yourself. Here is theorem 3.6. Let y be a discrete random variable with probability function py and mean ey equals mu. Then vy equals sigma square, which is equal to expected value of y minus mu square, and this is expected value of y square minus mu square. So here's another function. Variance of y is equal to expected value of y squared minus mu squared. Okay, why this is true? Actually, this is proved by expanding this thing. Sigma square, expected value of y minus mu squared, can be expressed this way. Expected value of y squared minus 2 times mu y plus mu squared, and here from the theorem 3.4 we can separate these, theorem 3.5, so this can be expressed as expected value of y squared minus the expected value of 2 mu y plus expected value of mu squared. And here you can by using theorem 2.3 and 2.4, you can get this constant outside, and this is expected value for constant, so this can be this. So here you can get the constant out from the expectation, and also expected value of the constant is constant. So and from here the expected value of y is mu, so this can be expressed as ey squared minus mu squared. Let's look at example 3.3. Use theorem 3.6 to find the variance of the random variable y in example 3.2. In example 3.2, we have discrete random variable y. The related probabilities are defined in table 3.3, and this time let's calculate variance using the formula theorem 3.6. First, we calculate the expected value of y, which is 1.75, and also we calculate expected value of y squared. And after the calculation, we can see that the result is 4. And using theorem 3.6, you can express this as this way. The sigma square is expected value of y square minus mu square, and this is 4 minus 1.75 squared, and the result is 0.9375. And actually, you also calculated this number from example 3.2, but you maybe find that this calculation is a bit easier than the previous calculation, and also this calculation used um, a lot, so it's nice to memorize this formula, and actually the proof is very simple. Okay, let's look at the example 3.4. The manager of an industrial plant is planning to buy a new machine of either type A or type B. If T denotes the number of hours of daily operation, the number of daily repairs Y1 required to maintain a machine of type A is a random variable. Um, Random variable with mean and variance both equal to 0.10t. The number of daily repair Y2 for a machine of type B is a random variable with mean and variance both equal to 0.12t. The daily cost of operating A is this. The daily cost of operating A, actually this is a function of random variable 10t plus 30y1 squared, and for B it's also a function of random variable. CBT is 80 plus 30 times y2 squared. Okay, and assume that the repairs take negligible time, and that each night the machines are tuned so that they operate essentially like new machines at the starting day of the next day, at the start of the next day. Which machine minimizes the expected daily cost if a workday consists of 10 hours and 20 hours? Okay, so the problem is we want to find the machine the minimizes the expected daily cost. So what we need to get is the expected daily cost, and expected daily cost is CAT for machine A, and uh, for machine B it's ECBT. So what you need to calculate is this one and this one, and compare the cost for 10 hours and 20 hours, and answer the lower number. Okay, let's calculate the expected value of cost A t. Actually, CAT, this is a function of random variable, and expected value of 10t plus 30 y1 squared. And by the theorem, it can be expressed as 10t plus 30 expected value of y1 squared. And uh, this one, expected value of y1 squared, by the formula that we learned in the previous theorem, it's sigma square plus mu square. So here, this yi squared, expected value of yi squared, it's sigma squared plus expected value of squared. So here is the sigma square, and here is expected value and squared. So the result is this one, 13t plus 0.3t squared. And what about the cost B? expected value for cost B is similarly, you can calculate this way, and from here you can also use this expected value of y2 squared. It's sigma square plus mu square. So here the sigma square for B and mu square for B, and as a result it is 11.6t plus 0.432 t squared. and the problem is for A, um, when t equals 10 hours, the cost for machine A is 160, and the cost for machine B, it can be calculated as 159.2. And since the machine B have smaller cost, we select machine B for problem A, and for problem B, we get the cost for machine A 380, and for machine B 404.8. So machine A have lower cost. So in this case, we choose machine A. Okay, that's all for now. Let's look at one more example from the exercise problem. Uh, Actually, this problem, this problem is for the discrete random variable case, and for the continuous random variable case of the same problem, which is the more generalized version. It's shown in the graduate school entrance exam in statistics department. So I think it would be nice to know how someone can derive this equation. So that's why I introduced this problem in this slide. Okay, let's go. If y is a discrete random variable that assigns positive probabilities to only the positive integers, show that this. And expected value of y equals sum of and actually here it have typo. It should be k. So sum of k equals 1 to infinity, and probability of y is greater than equal to k. Okay, and how can we prove this? And to get the intuition, it would be nice to enumerate the all these situations. So this is this way. So when k equals 1, it's summing up probability of y equals 1 plus probability of y equals 2 plus probability of y equals 3 plus probability of y equals 4 plus dot dot dot. And that's the situation when k equals 1. And what about k equals 2? That's probability of y equals 2 plus probability of y equals 3 plus probability of y equals 4 plus dot dot dot. And what about the situation for when k equals 3? That's this line, and when k is 4 is for this line. And is there any idea from here? I think some of you maybe already guess. However, let's what's expected value of y? That in discrete case, sum of y equals to 1 to infinity y times p of y, and actually this p of y is probability of y equals small y. Okay, and actually, if you look at this enumeration in this way, there's one probability of y equals 1, 1 p1, and if you look at this direction, there's 2 p2, and if you look at this direction and summing up them, it's 3 p3. So you maybe get it. So if you sum up this way, then that's exactly the definition of EY. Summing up y equals 1 to infinity y times py. So that's the solution for this problem. And if you write more rigorously, sum of k equals 1 to infinity, probability of y equals greater than k, it's actually equal to this. This one can be written as this. And also the inside of this is actually pj. This pj is the probability related to random variable y, and and summing up this way can be uh, reversed this way. So if you are summing up in different direction, if you are changing the sum of these two, if you are changing sum of these two, it can be converted this way, and this can be sum of j equals 1 to infinity j times pj, and this is expected value of y. So this is the solution for the problem 3.29. Okay, and here's homework for chapter 3.3. Thank you.